Symphony of the Seas displaces 900,000 tons, the equivalent of 6,500 fully loaded Boeing 747s balanced on open water. One rogue wave, one shift in load, and physics should send it to the bottom. But it doesn't. The trick that keeps this floating steel city from ever flipping comes down to a precise relationship between two invisible points, and it begins not with the ship's weight, but with its shape. A cruise ship like Symphony of the Seas is not just big, it's almost beyond belief. The ship's full load displacement comes in at over 228,000 metric tons. That's the actual mass of water pushed aside when this floating city settles into the ocean, and it sets the stage for every engineering challenge that follows. The popular claim that Symphony equals 6,500 fully loaded Boeing 747s is everywhere. But the real math tells a different story. A single Boeing 747-8 at maximum takeoff weight is about 447 tons. Stack up 510 of them, and you match the ship's displacement. Even at this corrected figure, the scale is staggering. More than 1,000 jumbo jets, all in one vessel riding the waves. The numbers are precise, the comparison concrete, and the result is a sense of mass that's hard to wrap your head around. Before any talk of buoyancy or balance, it's the raw weight, hundreds of thousands of tons, that demands an answer. How does something this heavy avoid sinking? A ship's ability to float comes down to a simple rule from ancient Greece, Archimedes' principle. When a cruise ship enters the water, it pushes aside a volume of seawater equal to its own weight. That upward force, buoyancy, doesn't care if the hull is made of steel, wood, or plastic. What matters is the shape. The wide, hollow hull of Symphony of the Seas acts like a giant container, forcing hundreds of thousands of tons of water out of the way. As long as the weight of water displaced matches the weight of the ship, the vessel stays afloat. Hull design is not just about cutting through waves, it's about maximizing the water plane area, the surface the ship presents to the sea at the waterline. A broad, flared hull increases this area, so even a small increase in draft adds a large amount of displaced water. For each centimeter the hull sinks, the volume grows sharply, and so does the upward push. This is why a cruise ship can be made of dense steel and still float. Its shape creates enough room inside to displace a sea's worth of water. The paradox isn't about weight, it's about geometry. Step inside the hull of Symphony of the Seas, and the first impression is not solid steel, but cavernous emptiness. Naval architect Mikhail walks the length of the lower decks, tracing a path past bulkheads and open spaces that stretch the full width of the ship. The hull is a vast, engineered shell. Its steel mass, about 80,000 tons, would be enough to build more than 40,000 mid-size cars. But it's what isn't there that matters most. The interior volume, nearly 650,000 cubic meters, could swallow over 400 Olympic-sized ice rinks. This hollow design is no accident. Every corridor, theater, and even the ship's ice skating rink adds to the internal volume that pushes water aside, generating the buoyant force that keeps the ship afloat. Mikhail explains that steel alone would sink instantly. But by shaping the hull to maximize empty space, designers turn dense material into a floating platform. The logic is simple. The more air and open volume inside, the more water is displaced, and the greater the upward push from the sea. It's a lesson in physical cause and effect, engineered on a scale that defies everyday experience. In the heart of the shipyard, the hull of Symphony of the Seas takes shape block by block. Each segment, weighing several hundred tons, is fabricated with millimeter precision inside a massive assembly hall. Lars, a lead engineer, stands beside a steel section the size of a small apartment building. explaining how every surface must match the digital model down to the centimeter. The workflow is a carefully synchronized dance. As soon as a block passes inspection, a gantry crane rated for 1,000 tons lifts it into the dry dock. The largest blocks, some over 20 meters long, are maneuvered into position with just centimeters of clearance, guided by laser alignment and GPS. This is not guesswork. The shipyard software predicts the final waterline within a margin of a single centimeter, even before the hull ever touches the sea. Lars points out that any deviation in block weight or fit could throw off the ship's balance, affecting how it floats and handles waves. The dry dock becomes a three-dimensional grid, each block assigned a precise location and orientation, with internal systems, pipes, wiring, ventilation already installed. By the time the last block is welded in place, the hull's overall shape, weight distribution, and stability are exactly as the naval architects intended. The result is a floating structure whose behavior in water can be forecasted with engineering certainty, setting the stage for the next phase, managing how the ship responds to real-world loading once it leaves the dock. Every cruise sets off a new calculation. As soon as passengers, crew, luggage, and fresh stores come aboard, the ship's draft, the depth below the waterline, shifts to reflect the added mass. On Symphony of the Seas, this relationship is precise. For every 190 tons loaded, the hull sinks by 1 centimeter. A full complement of guests, plus their bags and provisions, can nudge the ship downward by several centimeters before the first port is even cleared. Fuel adds its own rhythm to this balance. The ship burns through about 1,000 tons of fuel each day at sea, a figure nearly equal to the weight of 200 elephants. As tanks empty, the vessel rises slightly, regaining lost centimeters of draft. The waterplane area, the slice of hull at the waterline, acts as a giant lever, translating each shift in weight into a measurable change in how deep the ship sits. This is not a static system. The ship's equilibrium is alive, responding to every delivery, every meal served, every kilometer traveled. The hull's geometry ensures that even as weight moves on and off, the increase in draft brings a proportionally larger volume of water into play. Each new centimeter submerged means another 190 tons of upward force, keeping the vessel in a constant self-correcting dance with the sea. The numbers may shift, but the principle holds. The ship floats because every added ton finds its answer in displaced water. Elena, a stability engineer, stands in front of a cross-section diagram of Symphony of the Seas and points to the numbers that matter most. A beam of 66 meters and a metacentric height known as GM of about 2.2 meters when fully loaded. The beam is the ship's width at its widest point, and for a vessel this size, it's not just wide, it's deliberate. A broad beam increases the distance between the center of gravity and the metacenter, which is the key to self-righting power. GM, the vertical gap between the center of gravity and the metacenter, acts as a built-in safety margin. The higher the GM, the stronger the righting force that snaps the ship back upright when it tilts. On Symphony, a GM of 2.2 meters means the vessel can recover from a significant heel without discomfort for passengers or risk to safety. Heavy machinery, engines, fuel tanks, and ballast water sit deep in the hull, keeping the center of gravity low. This arrangement leaves a generous stability margin, measured and verified in every inclining test before the ship leaves the yard. Elena describes it as a safety buffer. Even if the ship tilts, the wide beam and low center keep the righting arm long and the recovery force strong. The numbers aren't just technical trivia. They're the reason a floating city can shrug off rough seas and remain steady, even when the ocean tries to tip the balance. The story of ship stability is written in both disaster and triumph. In 1628, the Swedish warship Vasa set out with a high center of gravity and too little ballast. Just minutes into her maiden voyage, a gust of wind pushed her to a heel of about 7 degrees. Water flooded the open gun ports, and the ship rolled onto her side, sinking in Stockholm's harbor before the eyes of a stunned crowd. The lesson was brutal. A tall, narrow hull with heavy weight stacked high leaves no margin for error. Modern cruise ships are the answer to that failure. On Symphony of the Seas, the center of gravity sits deep in the hull, heavy machinery and ballast forming a counterweight to the towering superstructure above. In rough weather, the difference is dramatic. During a Caribbean squall, Symphony heeled 15 degrees, enough to send loose items sliding and trigger alarms on the bridge. The crew activated the automated balance system. In less than 30 seconds, pumps shifted ballast water, and the ship returned to level. Most passengers never noticed the event at all. Elena, the stability engineer, sums it up. The physics that doomed Vasa now keep modern ships safe. Real-time sensors, wide beams, and low centers of gravity have turned a centuries-old risk into a managed routine. What once spelled disaster now triggers a quiet correction, proof that the evolution of naval architecture is not just about bigger ships, but safer ones. Every time a cruise ship like Symphony of the Seas sails, it proves that physical law, not luck, keeps a floating city upright. Engineering mastery turns principles like displacement and righting moment into everyday reality. In a world of ever larger vessels, the science of stability is more vital than ever. Thanks for watching.